start doing addition and subtraction formulas. Chapter 6 is beefy, I'm not going to lie. But. So, this one is a proof, not a verify, correct? So the first thing we do is grab a pen and not do that. All right. Left side, right side. This will help you for one of them that is on your sheet. So, first thing I do, rewrite cotan A cos cubed A over sine A minus sine cubed A, because I'm literally just rewriting the question. Now the left side, we could leave it as we want. The right side looks more crazy. I told you guys 98% of the time when you're stuck, it's because you don't GCF or factor, which is one of the questions on that little hand-in. You're going to have to GCF. So the top here is a cos cubed A. I got aggressively large writing here for a second. And then on the bottom, what can I do? Take out a GCF of a sine A. And then I'm left with 1 minus sine squared A. Now, 1 minus sine squared A needs to be an alarm bell in your head. That is Pythagorean Theorem identity turned around. Pythagorean Theorem identity turned around, right? So the Pythagorean Theorem identity is sine squared x plus cos squared x equals 1. I need 1 minus sine squared. So cos squared x equals 1 minus sine squared x, correct? So I can technically, in the next step, replace this with cos squared x. So I have cos cubed A over sine A, and then this is cos squared A. That's multiplied, that's multiplied. Are these all multiplied? Do I have any plus or minus signs in them? No. If I had plus or minus signs, could I cancel off? No. Because they're all multiplied, can I cancel off? Yes. This cubed is like saying cos A, cos A, cos A. So I can take 2 of these for 2 of those. And then what do I have? Cos A over sine A, which is? Cotan A. And then now a toddler could say, yeah, they match. And we can go left side equals right side. Do we agree? Yeah. Do you see the difference between verifying, proving? Verifying, proving. Do you see the difference? Yeah. Okay. My ultimate goal is that when the test comes, you can verify and prove. It's not that tomorrow you can verify and prove. It's not that the next day. It's when the test is next Wednesday, you can verify and prove. So sometimes it takes a bit of a struggle, of a couple days of struggling, and you will, and then all of a sudden it clicks because you practice enough of them, and they're just better. Trust me. The struggle is real at first, and then they click. That's what you have to do with proofs, just to practice a whole bunch. Okay? So you try the next one. Okay? It's very similar, it's just flip-flopped. Denominators and numerators. We'll go through example 7 tomorrow as our first example, just to practice, because these ones are the type of proofs for these ones are like basic sines and coses and tans. A lot of them are degree 1s. You just go to the top of the formula sheet and replace them, or you use Pythagorean Theorem identities. Because 1 minus sine squared is cos squared, I can replace it. All right. Formulas. Yay. So you have sum and different identities. We're going to come back to that tomorrow. We'll do a couple of those and then take them up each day as a little reminder. So sum and difference look way more complicated than they are. These are like my favorite formulas out of all of them. The reason why we have sum and different formulas is because they'll say determine the exact value of sine 15, right? The moment they say determine the exact value, that screams I can go to my unit circle and pull exact values off of it, correct? But if they say sine 15, can I pull 15 off of the unit circle? No. But it's best friends 45 minus 30 you can. 45 minus 30 is on the unit circle, isn't it? 45 minus 30 is what? 15. So that's why these sum and differences come out. They're all just the ones like 75. If I ask for sine of 75, exact values. You can't go sine 75 off your unit circle because it's not on there, but it's best friends 30 plus 45 are on it. Okay? So these sum and difference formulas are only used when it's asked to determine exact values of something that's not directly off your unit circle, but its best friends are. Okay? So we have sine A plus B. So an example, if it was sine A plus B, let's just pretend I was using sine 75 just to prove this. It'd be sine 30 plus 45. All I would do is for every A, I would fill in 30, and for every B, I would fill in 45. We agree? So ultimately, I would get sine 30. I'm going to put in brackets. Cos 45 plus cos of A, in this case would be 30, and then sine 45. So I literally just sine A, 30, cos B, 45, cos A, 30, sine B, 45. And I can pull those values directly off my unit circle, every single one of them. Does it make sense why these formulas exist? Just the exact value of something. So 30 and 45, 75, it can be any of those, right? And they ask for the exact value, but they're not directly off your unit circle. So we're going to look at cos 75. Can I do cos 75? No. But here it'll say use the sum and difference identities to find, or it'll say determine the exact value. That's another one that comes up. Determine the exact value. If you can just punch it in your calculator and get an answer, move on, question what the heck you're doing. Because they're not going to let you just go cos 75 and give an answer. That would be sweet, but that's more of a junior high question. So be suspicious if you can type it in and get an answer. Be like, probably have to do more than that. Okay? Cos 75. What numbers on my unit circle can get me there? Yeah. 30 and 45. There's actually more. What other ones could I do to get 75?
1 and 74.
Yes, but not helpful. Off the unit circle. It has to be numbers off your unit circle. So like 105 minus, or I don't remember what they are. 135 minus
120 minus 45.
45. Yeah, that would get you 75. Do I want to make it advanced and harder like that?
No.
No, but they could, right? They could. I'm like 30, 45 sounds good to me. We're going to go with that. But you can use more other two numbers on your unit circle to get 75, right? There's other ones on there. So I'm going to go cos. Now, this is what I'm going to do. I'm going to go cos 30 degrees plus 45 degrees. And to help me out, I'm going to line the formula underneath it. So what is the formula? It is cos A plus B. It's alpha plus beta, but I'm lazy, so I'm going to not use those. You could do x's and y's, whatever you want. Now the cos A plus B formula goes cos A, cos B minus sine A, sine B, right? So I'm going to write the formula. It is equal to cos A, cos B, and I like putting them in brackets because it helps me out, minus sine A, sine b. What matches up with A in this case? 30. And what matches up with B? 45. Could I do them out of order? It's 45 plus 30, still 75. Yes. Addition formula, it doesn't matter. Subtraction does. Because if you went, like, say you needed 15 and you did 30 minus 45, you'd have negative 15, which is not what you wanted to find, right? So subtraction, the order matters. Addition, you can put them out of order. It doesn't matter. I do know now, though, that my A matches with 30 and my B matches with 45, right? So when I go to write out my formula, I'm going to go cos 30 degrees plus 45 degrees. And I'm just going to match stuff. So cos 30 degrees, cos 45 degrees, minus sine of 30 degrees, sine of 45. Because this is the same as cos of 75, correct? So I can go cos 75 degrees equals. Now I go to my unit circle immediately. What the heck is cos of 30? What's your cos at 30? Root 3 over 2. And then what's your cos at 45? Root 2 over 2. Minus sine at 30 is a half. Sine at 45, root 2 over 2. When you do sum and difference formulas for sine and cosine, they will always result in common denominators. Greatest thing ever. If they don't, question yourself, because they need to. Okay? So let's see. We go root 3 times root 2 is root 6. When you multiply radicals, you multiply what's underneath by what's underneath, so under the radicand, and in front by in front. And then 2 times 2 is 4. Minus 1 times root 2 is root 2 over 4. And now we have a common denominator, which we will always have. If we don't, we did something wrong. So we're going to get root 6 minus root 2 over 4, call it a day. You just answered the question and gave an exact value. What is amazing about these is you can check them. Yeah?
No isolation.
No. That is as simple as it gets. If your square roots, you could cancel, like reduce them, then you would, but these ones we can't. Yeah? Yes. So we can check this. Go cos 75 in your calculator. If you go 75 degrees, go cos 75 in your calculator. Okay? Type that into your calculator. This should be the exact value of that. Make sure you put the top in brackets divided by the bottom if you don't use alpha y equals enter, if you don't use the fraction. Should be the same thing. So you should walk away from this question knowing, yay, I should be happy, or boo, I should be sad, try again. Right? There's no math enter button in the world that will turn cos 75's decimal into that. So you can't. So how will they ask the question? Most often they will not ask this as a multiple choice because you could just match what I just did, correct? They'll ask it as a numeric response, like square root of A minus square root of B, where A is greater than B over C, A, B, and C are, or something like that. Or they might go root 6 minus root B over 4, and what's B and what's B? Would be 2, right? So they make you actually find it, so you can't match multiple choice to answers, because you could. Okay, you guys try sine 195, sorry, 195. Find two things on your unit circle. We'll go through some of the TAM ones too tomorrow, but there's the two types of questions that you can ask in sum and difference. The first one is they ask you for like sine of 15 or cos of 15, and you just fill it into your formula, right? This is the second one that everyone forgets about in the sum and difference one, so I'm going to star it. So there's the plain one where it's like sine of 195 or cos of 15, you know, like we were just doing. This is the other part that everyone forgets about. You have to be able to spot these questions. So in chapter 4, we did this, but we did it with 1. Now we're going to do it with 2. So what the heck does that mean? So here it says cos A is 3/5, and cos is what over what?
Y over R, or
X over R.
X over R.
yeah.
Yeah. So this one's going to be x over r, and cos is, and a here is found between 0 and pi over 2. Your first thing you always have to do is draw the triangle in the right quadrant, and you would have done this in chapter 4. So we're going to have a triangle A. The triangle is always drawn towards the x-axis. So we know the angle falls between 0 and pi over 2, so I'm going to draw the angle, correct? It's just an arm that lands between 0 and pi over 2. And then I draw it towards the x-axis. This is triangle A. Welcome. Welcome, triangle A. And we're going to label it. We know x is 3. We know r is 5. We need to find y using Pythagorean Theorem. And the reason why we draw the triangles, we know that y is positive because it's here, right? So we're going to go y squared equals r squared, 5 squared minus x squared. So y squared equals 25 minus 9. Y squared equals 16. Square root plus or minus, square root plus or minus, y equals square root of 6, positive square root of 16, which is 4. To get triangle A. Then we have to get triangle B. Yep.
Because it's in a quadrant.
Oh,
It's in quadrant 1, so your y has to be positive, because here's y.
so
Your coordinate is 3, 4.
over R.
Like your coordinate is here, it's 3, 4. It has to be positive. Then we do triangle B. I'll do it in blue. Triangle B is found in quadrant 3. 3 pi over 2 and 2 pi. Actually, quadrant 4. That's a lie. It's in quadrant 4, so it's here. And I draw it towards the x-axis. And it's triangle B. And it's x over r as well, because it's cos. Right? So x in this case is 5. R in this case is 13. And y is not sure, but I do know that it's negative because it has to be in order to be in quadrant 4. Right? That's why we draw them. Then I just use Pythagorean Theorem again. So I'm going to get y squared equals r squared, 13 squared minus 5 squared. Y squared equals 169 minus 25, which is 144. And then I square root it, and I get plus or minus, but in this case it's negative 12. So you did this in chapter 4, where they would give you a trig ratio and then send you to a certain quadrant, and then you would get another trig ratio. They often made you find the other 5 trig ratios, right? You did that in chapter 4. This one wants, so we do that the exact same as chapter 4. This one wants cos A plus B. Okay? This is where it goes awry. Cos A plus B is not cos A plus cos B. You can't distribute it in. It has a formula that goes with it, doesn't it? If you can get to this step and fill it into the formula, you'll get the question right. It's just remembering there's a formula. Cos A plus B has a formula. It's cos A cos B. Cos A cos B minus sine A sine B. What's cos of A? We literally now just need to fill in these 4 brackets. What's cos A? It's given to you at the top. Cos A equals 3/5. So instead of putting cos A now, like this is cos A plus B, right? That's this. Cos A is 3/5. So I can take cos A, I can toss it behind my head and replace it with 3/5. What's cos of B? 5/13. It's also given to you. How do I get sine of A?
Take the y values, and then put it over r.
Yeah. So I go to my A triangle and I go 4/5. And then sine of B?
12/13.
Negative 12/13. And then I should get common denominators or I'm doing something wrong. I'm going to get 3 times 5, which is 15/65. And then minus negative 48/65, which actually results in 63/65. So do you see how you have to draw the first two triangles? Because you're going to have two of the trig ratios, but you're going to need the other two by finding the third side. So it uses chapter 4 to do this outcome. I'm only going to give you some of these because I didn't even do the tan ones. So I'm just going to give you the sine and cos ones and then one like this. Because I can't assign more than that, we haven't done it. So, just going to give you page 306, number 8. Now, what if I gave you cosecant of 15, let's say? Cosecant is, 1/sine, correct? So could I not just find sine of it and then flip the answer? That's it. That's all. It's nothing crazy. Like, don't overthink it.
So like r/5.
Yes. That's it. So 8, and then I want you to do 20A and B. So it's not crazy. And like I said to you, I'm here tomorrow at lunch at London, right? I'm just trying to get you guys to have all your stuff